Welcome everyone to the HERE Exposomics webinar on next generation tools for measuring exposure to air pollution. If you have any questions during the talk, please put them into the Q&A box. We're very excited to have Dr. Thomas Riley and Dr. Jessica Treiner from Access Sensor Technologies as today's speakers. Dr. Riley is the CEO of Access Sensor Technologies. He has expertise in instrumentation, analytical chemistry, and material science. Since 2020, he has been the CEO of AST, which is a spin-out from Colorado State University, focused on developing and commercializing new tools for pollution monitoring applications. Dr. Treiner is the Director of Research at Access Sensor Technologies. She has expertise in air sampling, low-cost air quality sensors, and aerosol physics. Dr. Treiner received her PhD in mechanical engineering from Colorado State University, where many of the air sampling instruments sold by Access Sensor Technologies underwent their initial development. Welcome, Dr. Riley and Dr. Treiner. Thank you.
Thank you, Susan, for the introduction. Today, we're going to start by reviewing why we care about measuring air pollution and why we care about measuring personal exposures to air pollution in particular. Next, we'll talk about the approach that we've taken at Access Sensor Technologies when developing instruments for this purpose. After that, we're going to spend most of the webinar discussing studies that highlight recent advances in air pollution exposure assessment. These studies have all used instruments that were developed by Access Sensor Technologies using SBIR funding from the National Institute for Occupational Safety and Health, as well as the National Institute of Environmental Health Sciences. The first application we're going to talk about is a large-scale global field campaign that characterized personal exposures to household air pollution. Second, we're going to talk about a study in which researchers mapped the oxidative potential of particulate matter air pollution across 2 Canadian cities. Third, we're going to talk about characterizing personal exposures to particulate matter air pollution by microenvironment. And fourth, we're going to talk about efforts to characterize personal exposures to multiple air pollutants, including both particle and gas phase pollutants simultaneously. Finally, we'll talk about how the research highlighted in these 4 examples has informed our current efforts to develop new technologies for air pollution exposure assessment. So, why do we care about human exposure to air pollution? We study air pollution because exposure to air pollution is the second leading risk factor for disease and premature death worldwide. And among the subset of global burden of disease study risk factors that are characterized as environmental and occupational risks, exposure to air pollution is the #1 risk factor. Most of this risk is attributed to fine particulate matter air pollution specifically. That means particles that are suspended in the air and have aerodynamic diameters smaller than 2.5 micrometers. These small particles can penetrate deep into human lungs when they're inhaled, and they're associated with a lot of health problems. Fine particulate matter is typically abbreviated as PM2.5, like you see here. And most people around the world live somewhere where the outdoor PM2.5 level is considered unhealthy. This graph illustrates estimates of human exposure to PM2.5 that were developed for an earlier iteration of the Global Burden of Disease study using a combination of satellite data and outdoor ground level monitoring data. The x-axis on this graph, which is on a log scale, denotes increasing outdoor PM2.5 concentrations. And the y-axis denotes the proportion of the global population living in a location where the annual average outdoor PM2.5 concentration is equal to the value on the x-axis. You can see distributions for the 10 most populous countries in 2013 shown in different colors, along with a distribution for the rest of the world shown in gray. The authors of this study estimated that in 2013, 90% of the global population lived in a location where the annual average outdoor PM2.5 concentration exceeded the World Health Organization air quality guideline of 10 micrograms per cubic meter. Today, these data are a little more than 10 years old, and in many places around the world, ambient PM2.5 pollution has been declining since 2013. But the average annual population weighted exposure to outdoor PM2.5 pollution is still above 30 micrograms per cubic meter globally. And in 2021, the World Health Organization reduced their guideline for annual average PM2.5 exposure to 5 micrograms per cubic meter. So most of the world still lives with outdoor air pollution levels that are considered harmful to human health. And there's also a few limitations associated with these estimates. First, most of the ground level measurements used to develop these estimates come from high income countries. So exposure estimates for people living in low and middle income countries are subject to greater uncertainty. And all the data that I've shown you thus far are on outdoor air pollution levels, because that's most of what we know about human exposure to air pollution, where someone lives and what the outdoor air pollution level is in that location. But there's usually more to the story than that, and that's why we care about measuring personal exposures to air pollution. Here on the y-axis, you can see a set of 120 24-hour average personal exposures to PM2.5 that we recently measured among adults living in California's Central Valley in collaboration with Colorado State University and CCEJN. And on the x-axis of this graph, you can see the average outdoor PM2.5 concentration measured over the same 24-hour period by the outdoor monitor nearest to the person's home. The diagonal dashed line here is y equals x. And you can also see horizontal and vertical dotted lines that denote the US EPA 24-hour air quality standard for PM2.5, which is 35 micrograms per cubic meter. You can see here that personal exposure was rarely equal to and was often higher than the concentration measured by the nearest outdoor monitor. For this data set, the median difference between the 24-hour average personal exposure and the 24-hour average outdoor measurement from the nearest monitor was 4.5 micrograms per cubic meter. So why aren't personal exposures equal to outdoor levels? The answer is because people are exposed to air pollution from a lot of different sources and in a lot of different places. People are exposed to outdoor ambient air pollution, but people tend to spend a lot of their time indoors and actually spend the majority of their time inside their own homes, where they're also exposed to air pollution from indoor sources. One common source of indoor air pollution, for example, is cooking. People that cook using solid fuels like wood are exposed to a lot of particulate matter that's emitted from the combustion of that fuel. People that cook with gas tend to be exposed to less particulate matter, but can be exposed to high levels of nitrogen dioxide, which are emitted during the gas combustion. And even if a person cooks using electric appliances only, in which case there are no indoor emissions associated with the energy source being used to cook the food, there's still exposure to PM2.5 that's emitted from the cooking food itself. People are also exposed to particulate matter, air pollution, and other air pollutants at work. For example, people that work in construction, mining, or agriculture can be exposed to dust. People that work in agriculture can be exposed to pesticides. And people that work in a variety of occupations, but especially in healthcare, can be exposed to airborne pathogens like SARS-CoV-2. So there's a lot of sources and a lot of settings where that contribute to human exposure to air pollution. And now I'm going to hand the presentation over to Tom for a bit, and he's going to talk about some different measurement techniques for assessing personal exposure to air pollution.
Thanks, Jessica. So it's important to spend just a minute or two discussing terms that are often interchanged. And this is the discussion around sampling approaches to understanding exposures and pollution levels, and sensing approaches. And they both have advantages, and in many ways they complement each other. So you'll see in sampling is where many of the regulatory rules have been written, because it dates back, in many ways, it predates all of the modern sensing technologies that we have today. And so in this middle picture here, this is a very typical and minimal layout for estimating the particulate matter exposure in an individual's breathing zone. And so you'll see there's a small sort of teal blue circular inlet. And what that's going to do for us is those are very carefully engineered to size select for certain size distributions of particulate matter. Below that, in that same blue little teal inlet, is a cartridge holding a filter. And that filter is where we're going to physically collect matter onto that. So we've thrown away, in many instances, you throw away the very large particles that are not able to really get deep down into the lungs. And so that we're focusing often on things like PM 2.5 and below, or sometimes for occupational applications, you'll hear the term respirable used quite a bit. And that's essentially trying to focus in on the particles that really can engage in the lungs, deep into the lungs, and are linked most strongly with chronic health effects. But then you'll see there's this tubing that snakes across this person's torso, and then down to their hip is a sampling pump. And this is typically based on technology that's 30 or 40 years old. And so if you're not familiar with this technology, some of the most common places you'll see similar things are in aquarium pumps. So if you've ever been around an aquarium, you'll typically be able to hear that pump, and you'll maybe notice the vibrations and the pulsation around that technology. And so that's it's been used extensively for the last 40 or 50 years. But on the right side, we have this sensing approach. And sensors have now become so ubiquitous in our world that I think in many ways we take them for granted. And in the personal exposure applications, sensing, it can be quite useful, because now rather than building on a technology stack that's 40 or 50 years old, many of these designs are based on much newer technology. They're smaller, lighter, energy efficient. But really critical to thinking about sensors is you want to ask about things like the accuracy and the specificity for the compound or compounds that are under investigation. But they do have great benefits. Oftentimes they'll be paired with some kind of geolocation, or they'll be logging data that will allow you to see how exposures happen through time in a qualitative way. And so these two things you can see are sort of complementary. The filter samples that get collected for particulate matter can be analyzed really in almost countless ways. But you'll just get that one sample. You'll just get that one item to send off to the lab. So you'll, most of the time, not really gain much insight into the where and when of the exposure. But this is really why our company exists, and how we came into existence was really around this core idea. So if we go to the next slide. What we've licensed from Colorado State University and commercialized was, our first product was something we call the UPass. So let's step through this slowly. The ultrasonic personal air sampler. So it's ultrasonic because we don't use the technology that is based on a diaphragm pump. We use very tiny piezo pumps. And what a piezo material is something that we can drive at a very high frequency. And so we eliminate the pulsation effect of having to sort of wear an aquarium pump throughout one of these exposure assessment periods. And it is also the reason ultrasonic is these pumps oscillate at frequencies that are sort of above the human limit of hearing. And so we don't really notice them. And so the benefit is it sounds like just a quiet white noise machine is in operation rather than something that pulsates and can become a little bit cumbersome and objectionable depending on the cohort of people that you might be studying. And so another point is, you'll notice on that previous slide, we had that inlet and tubing and sampling pump, and these were all distinct items. Whereas the UPass is a fully integrated device, and this is very intentional. So we have a custom engineered series of inlets that give us those size fractions of particles we want. And then below that, we have a cartridge with our filter. And then below that is the entire balance of systems. So all of that is fitting into one small device. And not just to mimic a sampling pump, but to really augment it in ways that give us environmental information and allow us to have modern microcontrollers on board to really customize the type of sampling session that you want to configure. So it's a very highly configurable system, which many of our customers have used with great success. So, but remember on the last slide, we talked about there are a lot of benefits to the sampling in combination with sensing. And so our following product that we released just a couple of years ago is something we call the UPass V2.1 Plus. And so really the big part of that plus is that we've added an optical particulate matter sensor. So now we don't have to give up that time-based sensing to understand some of that where and when exposures happen. And the combination of those two becomes really powerful because now we can estimate both where and when particle exposures happen, but also that filter can still go off for that very detailed gold standard analysis, whether it's for regulatory applications or, as we'll talk about in a few slides, some of these really interesting and creative methods of analysis of those filter samples. And so this is something that we've just been truly wowed by so many of the research groups around the world. And all told, these samplers have been used for millions and millions of hours at this point. So even though it's a fairly new technology compared to some of the other hardware that's out there, it's really shown to be quite robust. So I think Jessica is now going to tell you a little bit about really some of our earliest adopters in this technology.
Thank you, Tom. The first exposure assessment application that we want to talk about today is the Pure Air study. And this was really the first research study to use the UPass. Over a 28-month period, the Pure Air study team used UPass to collect 998 personal samples of PM2.5 exposure and 2,541 samples of in-home PM2.5 levels in 120 communities. These 120 communities were selected from the 8 countries that are shown here on the map in red. And these 8 countries were selected because there was a lot of variation within these countries of the primary cooking fuel used by different households. As far as personal and in-home air sample collection goes, the Pure Air study was a massive undertaking, and it resulted in a massive data set. The study team themselves noted that the Pure Air study was among the largest and most diverse assessments of PM2.5 and black carbon exposure related to household air pollution to date. This study represented a large step forward in terms of our understanding of how much PM2.5 pollution people are actually exposed to around the world, especially in low and middle income countries where outdoor monitoring and personal exposure data are more scarce. The Pure Air study team noted that their data set more than doubled the number of measurements, PM2.5 measurements specifically, in the World Health Organization database on household air pollution. Prior to this study, that database contained approximately 2,200 measurements that were collected across 44 different studies, whereas the Pure Air study team, they collected 3,500 measurements in a single study. And they accomplished all of this using the UPass. The Pure Air Study team reported that the UPass was easy to use and that it was widely accepted by the individuals who underwent exposure assessment as part of the study. They reported that 95% of personal samples collected with the UPass included GPS data points recorded away from the participant's home, which suggests that study participants wore the UPass inside their homes, outside their homes, and away from their homes. The Pure Air Study team also highlighted how the detailed sample log files recorded by the UPass contributed to their high sample success rate by enabling rapid quality assurance. Here you can see a screenshot of just a portion of a UPass v2.0 log file. At the top of this screenshot, you can see a summary of the sample, which includes the start and end times, the overall sample duration, the starting and ending battery stated charge, the average air sample volumetric flow rate, and the total volume of air sampled. Below that, you can see the sample log. The sample log records UPass operational parameters at 30-second intervals throughout the full duration of the sample. The information recorded there includes the air sample volumetric flow rate at each 30-second interval, as well as the UPass GPS location if the GPS is enabled and the GPS is able to obtain a signal at that 30-second interval. So during the Pure Air study, researchers who were working in the field uploaded a log file like this one to a central project server after each sample was complete. And every 24 hours, an R script was used to check the server for new log files to identify samples with possible errors. The Pure Air samples were programmed to run for 48 hours at a sample flow rate of 1 liter per minute. So the R code looked for samples with durations of less than 43 hours or with sample flow rates of less than half a liter per minute. And any sample log file with one or both of these issues was brought to the attention of field staff immediately so that a repeat sample could be collected promptly. Out of the more than 3,000 samples that were collected in the Pure Air study, though, the investigators reported only experiencing about 300 sampling errors, which, a 90% sample success rate is very high for in-field collection of in-home and personal air samples. Since the Pure Air study was completed, we've developed a software package that makes it easier to work with UPass log files in the R programming environment. The functions in this ASTR package can be used to read the sample summary data from a UPass log file and format it for analysis using a single line of code. Additionally, the time resolved sample log data, those values that are recorded at 30-second intervals, you can use the ASTR package to read in the entire sample log from a given sample and format it for analysis with another single line of code. If you want it to read in the sample summary and log data from, say, 3,500 UPass log files, combine them all and format them for analysis, you could do that with about 7 lines of code with the ASTR package. If you don't have experience writing code in the R programming environment, or if you want to just perform some quick quality assurance checks on a dozen or so log files while you're in the field, we've also developed a free web-based R Shiny application with a graphical user interface that you can use to quickly summarize UPass log files in a web browser window. Here you can see that I've uploaded 4 example log files, and this table on the sample summary tab is showing that each of these samples ran for 24 hours with an average flow rate of 2 liters per minute as intended, and that each sample shut down once the pre-programmed duration was complete. The Shiny app also includes an interactive plot tab shown here where you can create and view simple graphs of sample log data over time. Here you can see time-resolved optical PM sensor data that was recorded over the duration of 2 co-located indoor samples. Additionally, there's a GPS map tab where if the UPass GPS was enabled and was able to obtain a signal, you could see locations on a map where UPass data were recorded during the sample. So overall, we're continuously working to develop new and better tools for rapid and robust air sample quality assurance to enable larger scale personal exposure assessment campaigns.
So in the next example, we want to show some of the creativity that our customers have demonstrated, which didn't occur to us at the time of creating these products. And so in many ways, this is a little bit like the invention of ride sharing apps when the people that invented smartphones probably did not see that one coming. But when you combine all of the attributes of these products, you end up with something new and different, and people get creative. And so in this example, we've got 2 Canadian cities, Toronto and Montreal, being mapped by some of, again, our earliest customers. And part of what is so exciting to us about this is they said, we'd like to map really the composition and oxidative potential of particulate matter as it's spread across these cities. But they're just a small team. But with the tools we have, they took advantage of the programmability of these devices and the fact that these devices keep very accurate time on board the hardware without needing to be tethered to phones or other timing sources. And so they set up a 70 sampler network across these cities and collected samples for 2 weeks. And from that, they were able to use those samples and not just measure the mass of particulate matter, which is important and is done constantly, but they were able to then add on another interesting measurement technique of doing both the oxidative potential and looking at the reactive oxygen species that are generated from that particular matter. And so the reason that that's so exciting is that it's digging down a layer from not just having a mass of particulate matter, but also looking for some of the behavior of those samples that are linked in a causal way to negative health effects. And so now they took these samples, again, with a very small team. And then as they layered across, they were able to generate a heat map of the different corridors of high reactive oxygen species generation and high oxidative potential. And essentially what that allows them to do is make both modeling and forecasting models available, but also you've got the potential to really inform targeted policy and play a very active role in how smart cities evolve in both looking out for the health of their citizens, but also being mindful of the activities that are core to these cities. And so in these instances, they were able to identify things related to non-tailpipe emissions and related to trains and rail yards, and it was really just a wonderful demonstration. And I should say, this one this study was done in a stationary manner. So even though our tools are small and light and they're generally worn, similar to the last study, a mixture of stationary, and we see our customers do a mixture of stationary and personal exposure monitoring. And in this instance, that stationary network is what allowed them to build this interpolated heat map of essentially where these ROS and oxidative potential activities are highest.
Now on to our third example application. Earlier, I emphasized that personal measurements are important because people aren't just exposed to outdoor ambient air pollution, they're exposed to pollution from a lot of different sources in a lot of different settings. So now I want to talk about how time and location resolved particulate matter data can be used to examine the proportion of personal exposure used in different environments. In this study, we collected personal filter samples with the UPass because we wanted to analyze physical samples of air pollution for certain constituents. But we used the UPass v2.1 Plus, which also logs time-resolved GPS and optical PM sensor data. So we took time-stamped GPS and PM sensor data recorded during 224-hour personal samples, and we used a clustering algorithm to identify distinct locations where each person spent time during each sample. For the example shown here, the algorithm identified 4 distinct clusters of GPS points, one corresponding to a home, one corresponding to a transit station, one corresponding to a store, and one corresponding to another residential location. And here you can see the fraction of PM2.5 exposure that this individual was estimated to receive in each of these environments. And these exposure estimates were obtained by apportioning the optical PM sensor data recorded during the sample. One point that you might have taken away from the graph on the previous slide, and that I want to emphasize here, is that a lot of exposure to air pollution occurs inside the home, whether that pollution comes from outdoor sources or indoor sources. So mitigating pollution sources around and in the home is really important if we want to reduce personal exposures. On this graph, each of the 200 personal samples from this study is represented by a single data point. On the x-axis, you can see the fraction of time that the individual spent at home during the 24-hour sample. And on the y-axis, you can see the fraction of PM2.5 exposure that the individual was estimated to receive inside the home from the optical PM sensor data. Most study participants spent most of their time and received most of their exposure inside their own home. In this study, the median fraction of time spent at home was 90%. Now, 43% of these 200 samples were collected with a participant who was not employed outside the home. Of this 43%, most were either full-time homemakers or retirees. However, other recent studies of personal exposure by microenvironment in the United States have reached similar conclusions. Even studies where all participants were employed outside the home at a job that they commuted to, these studies of personal exposure by microenvironment typically find that most people spend most of their time at home. And therefore, it's often the case that most exposure to particulate matter air pollution occurs inside the home. So overall, results from this study and others emphasize the importance of reducing exposures to pollution in the home environment. I also want to talk a bit more about this subset of samples in which the participants spent less than 85% of their time at home. And for these samples, the proportion of PM2.5 exposure received inside the home was lower than the proportion of time spent in the home. And that implies that the individual experienced higher PM2.5 exposure somewhere else. So let's take a look at the proportion of exposure that was received in different environments for this subset of 28 samples. On this plot, the fraction of PM2.5 exposure is on the y-axis, and each bar across the x-axis represents a unique 24-hour personal sample. The different colors within each bar represent proportions of exposure that were estimated to be received in different types of environments using the time-resolved GPS and PM sensor data. And if you see a black bar drawn around part of a bar, a black box drawn around part of a bar, it means that is suspected to be an occupational exposure, given the type of environment, the amount of time spent there, and what the participant told us about their occupation. Across these 28 samples, the two largest non-home sources of exposure tended to be transit and agricultural environments. This subset of samples included a larger proportion that was collected with individuals who worked outside the home, and a larger proportion that was collected with individuals who worked in agriculture, which emphasizes the relevance of occupational exposures, in addition to in-home exposures, among this group of adults living in urban, peri-urban, and rural parts of the Central Valley. So overall, this illustrates how time and location resolved personal exposure data can be used to identify and target specific environments where there are the greatest opportunities for exposure reduction.
So in our last example, we're going to talk a little bit about how, again, some of the creative questions that we fielded from our collaborators and customers, and how we've tried to address those needs. And so we started out discussing this hardware, talking about an inlet, which below that inlet, which helps us separate out particles of different sizes, sits a cartridge. And in that cartridge sits our filter, which we have to keep in a very, very pristine environment, because that's where our particles are showing up. And so we need to prevent extraneous material from interacting with that filter. But we were asked, it seems like there's an opportunity there. Could we add something to that stack of materials that would capture volatile or semi-volatiles? And so this is something we've dubbed the sorbent packet that we place below that particulate matter sampling filter. And we've managed to do that with sort of modest modification to the cartridge. So now in the center of this slide where you see number 2, you'll see that cartridge, even with this slightly more complicated stack, still fits under that size selective inlet. It still threads together onto the device. And one of the things that we've been involved with is, asking the initial question, because this is not, we're in the field of high performance instrumentation. And so the first question you need to ask is, does this have an effect on the particulate matter sampling capability? And so Jessica's prepared a slide showing that whether you're sampling for PM 2.5 or a larger size fraction, PM 10, we see tremendous correlation with or without this sorbent packet. And so, we're quite confident that we can sort of get this 2-for-1 arrangement without impacting the kind of gold standard particulate matter sampling. Well, so no, this opens up a tremendous new world of opportunities, because there are many specialized sorbents out there in the world. They can be tuned to focus on different classes of small molecules and gases. Certainly, it opens up the research community to be creative in thinking about specialized adsorbents that can be used. And this image, borrowed from the publication listed down below, is just another reminder of the huge opportunity that lies ahead of us compared to where the methods and science that has been established. And so this webinar series has had many exposomics presenters, and there are many new initiatives happening in that space. And our tools, we love to see that our tools are experiencing that uptake with those researchers as well, because part of what you need to be able to do, characterization beyond just particulate matter or beyond just elemental composition, but if you want to start looking at the and the biological nature of the environment that we exist in, or an individual exists in, well, you need to be able to have a sample that you can extract and then run through these more sophisticated technologies, like in this example, next-gen sequencing. We're seeing, and we're seeing a lot of really exciting work, people looking at working with pregnancy cohorts, where women are being tracked during their pregnancy, and using these tools. And the way I like to think about it is that we are getting to finer and finer resolutions about the external environment that we live in, and moving beyond some of these general topics like particulate matter. And we're probably going to see an evolution of discussing not just particulate matter, not just diesel soot, but we'll continue to see finer and finer resolutions there. And the exciting thing for me is that it gives the opportunity for the environmental scientists to try to play catch up a little bit with the metabolomics and genomics and epigenomics world, because really we want to see how all these particulars are pushing and interacting on the human being as an organism, and how all of this chemistry ties together. And so it's really a tremendous time to see so many new research ideas coming out of, or at least where our tools can be enabling to help pursue some of these interesting research hypotheses.
Thank you, Tom. I'm going to wrap up the presentation now by talking about future directions that we're moving in. We're currently working on developing new tools for exposure assessment that can sample and sense multiple and particle gas phase pollutants simultaneously. So, this ties back to the ideas that Tom was just expressing about, trying to capture and characterize more of the exposome. One instrument that we've developed recently is called the Home Health Box. This instrument is approximately the size of a toaster, and it's designed for indoor stationary measurements. Recall how I emphasized earlier that people spend most of their time and therefore often receive most of their exposure at home. So characterizing exposures in the home environment is really important. The Home Health Box can collect up to 2 particulate matter samples simultaneously. So you could sample onto 2 different types of filter media to analyze your samples for different constituents, or you could sample 2 different PM size fractions, say PM 2.5 and PM 10. The Home Health Box can also collect up to 2 gas samples simultaneously. So again, you could install 2 different sorbents to sample different pollutants. In this photograph, I've shown the sorbents that you would use if you wanted to sample aldehydes and VTEX respectively. Additionally, the Home Health Box can be configured with a suite of low-cost sensors to log time resolved data on estimated fine PM levels, CO2 levels, NO2 levels, and potentially levels of other gaseous pollutants. Historically, if you wanted to measure all these things in an indoor environment, someone would need to go on site and set up a whole bunch of different instruments. Whereas we've designed the Home Health Box to collect a lot of samples and a lot of sensor data using a single self-contained and virtually silent instrument that can be programmed in advance to start, sample, and then shut down automatically. And the idea here is that you could prepare a Home Health Box sample in your lab, ship it to a location to be monitored, and all the person who receives it at that location would need to do is unpack the Home Health Box, plug it in, turn it on, wait for it to run, and then let it shut off before packing it back up and shipping it back to you. So it's designed to make the process of indoor air quality assessment much more efficient, to therefore make it possible to increase the scale of indoor air sampling. On the wearable side of things, we're also working on advancing the development of an instrument that was initially developed at Colorado State University that's called the AirPen. The AirPen samples particulate matter onto a filter while sampling gaseous pollutants onto a sorbent tube in parallel. So again, trying to sample both particle and gas phase pollution using a smaller wearable device. Like the UPass V2.1 Plus, the AirPen also includes a low-cost optical PM sensor, a low-cost total VOC sensor, a GPS module, motion sensors, and a light sensor to facilitate time and location resolved personal exposure assessment. So overall, moving forward, we're trying to facilitate more comprehensive assessment of multi-phase pollutant mixtures. Thank you for taking the time to attend our webinar today. Please let us know if you have questions, and if you'd like to learn more, you can check out our website as well as these two public Zotero libraries of studies that have used the UPass and the Home Health Box. In both of those libraries, there are a lot more really exciting exposure assessment applications.
Thank you so much, Dr. Riley and Dr. Treiner. Very interesting talk. So if you have questions, please put them into the Q&A box, or if you'd like to ask your question, just raise your hand and someone will unmute you. I've got a question for you. So if you're wearing a device, does the person also keep a diary of their activities that you can correlate to your measurements?
Historically, that is a technique that has been used in a lot of studies. That is a common practice for someone to wear a monitor and then to keep a diary of activities. So that can be really helpful to gaining insight into sources of personal exposure. The disadvantage of that is that it imposes an additional burden on the person who's undergoing exposure assessment, so they have to keep the diary. And so, part of the idea with the, modern electronics, typically including GPS sensors and, light sensors and motion sensors, is that, we might be able to get away from the asking people to record time activity diaries and using more sensor data to see where and when exposures occurred. So there's definitely advantages to time activity diaries, but they do potentially impose an additional burden on people. And so, we can hopefully use more sensor data to get away from that or reduce the importance or the burden of that.
That would be great. I believe our Q&A box is experiencing difficulties. So if you have a question, just raise your hand. And I think, Liz, will you?
Yes, and actually we have Elaine Fostman who has a question, so I'm going to unmute her just now. Go right ahead, Elaine.
Great, thank you so much. What a great presentation, and really interesting to see the different sizes and capabilities of the sensors. I had two questions. One was, have you you showed how you could refine exposures on a personal level by getting the input from the inside of the home. Have you looked at the match ability with these prediction models that are using the information that's collected in the few monitors that are around the US to calculate exposures for particulate matter? And air pollutants in general? There's been a lot of discussion how useful those are or not. And the second question is, I wanted to know your assumptions when you did you did oxidative stress. No, you did reactive oxygen. I can't remember what your combined impact was. When you did that, did you do an additive model, or did you proportionally add components based on their potency? like the PM 2.5 versus another air pollutant? Thanks. Really great presentation.
So is the first, let me make sure I understand both questions. So is the first question about how well personal exposures are related to outdoor levels?
No, I think you showed that pretty dramatically
Yeah.
on that. But there are models that people are using now for external as well as internal that are more rough estimates. But I don't have a feeling for how far off they can be. And with your techniques, you actually could probably give that, well, the uncertainty range is such and such to such and such. Have you done that or not yet, or have a sense? Yeah.
Yeah, no, I don't have, I don't have data on that, on how personal exposure data that we've collected relates to exposure estimates from models, like models that are based on sort of try to fill in the discrete outdoor measurement data. The second question about the oxidative potential, I can talk a little bit about this, and Tom might be able to answer more. That wasn't done by us personally. That was done by some customers of ours at McGill University. So I can go back to the citation for that so you can see it, because there's more in the publication about, too far back, sorry. This Ripley et al. Publication about the approach that they used. So my understanding is they used an existing model for reactive oxygen species, and the inputs to that model were I believe the iron and copper content of the particulate matter. So they collected the physical samples of PM. They used X-ray fluorescence to measure the iron and copper content of that particulate matter, and then those values were then input to a reactive oxygen species model. So that was where these values came from. And then for the oxidative potential, that was a different measurement where they actually extracted the PM and put it in like a synthetic respiratory tract lining fluid, and then measured how much of that PM when put in the fluid depleted different antioxidants. But I don't personally have experience doing those sorts of measurements. Tom, do you have anything to add to that?
I think you did a great job summarizing it. It's one of the places where I think there is still those measurements are still fairly difficult to do, and so it's laudable anytime folks try to analyze a large sample set with that, because you're back to the lab doing fairly serial laboratory steps in order to get that have those measurements done in a reproducible way. So it's something that I think there's this very interesting spectrum of totally non-destructive techniques, semi-destructive, or depending on how things are handled, all the way down to fully destructive sample analysis, where the sample is extracted and run through HPLC mass spec or GC mass spec.
Great, thank you. Any other questions? We're just about to 3 o'clock. Okay, well, thank you so much, Dr. Riley and Dr. Treiner. Very, very interesting talk. And I hope everybody enjoyed the webinar, and we don't have a date for our next webinar, but please stay tuned. And thank you. I hope everyone has a good afternoon. Bye.
Thanks so much.